Okay, so I hope recording is okay by everyone. We continue the discussion of Bayesian network today. So by way of reminding, a Bayesian network captures some of the independence in the system, or some of the dependence, whatever, in whichever way you want to think about it. Not necessarily causal dependence, but based on intuition that has to do with what affects what. So this is an example people use in the literature a lot. There's rain, as a result, the floor is wet, as a result, someone sleeps. Okay? Now, so the intuition of what I'm going to talk about today, I'm starting to talk about independence. Essentially, Bayesian network is attempting to code some independence in the distribution of all the variables we are interested in, or conditional independence in general, so that we can reason about the distribution of all of the variables. Okay, and so let's think about this example. If the floor is wet, then intuitively rain and sleeping no longer is connected, because a person will, fall because the floor is wet. It's no longer relevant. Raining becomes irrelevant, so to speak. So this is the intuition of the conditional probability we want to be able to read out of the network. Below here are the two possible formal definition of what is conditional probability in the context of this network, so that the intuition will be clear. So given that the floor is wet, the probability of rain and sleeping equals to the product of these probabilities. So rain and sleeping could be, it's raining and a person fell, it's raining and a person did not fall, whatever. Doesn't matter what we're talking about, but this condition should hold, and then we would say that the two variables R and S are conditionally independent depending on W, which is the intuition we talked about just a minute ago. And here is another way to say it. If the conditional probability of falling, depending on the fact that the floor is wet and there's raining, well, you can drop the raining, it doesn't matter. So it's equal to this. Okay? As an exercise for yourself, you can try to see when these two are equivalent. And if they are equivalent, determine to yourself if these are equivalent or not. But these are two possible definitions of conditional probability. So they should be equal. Okay, so that's the background. Now I want us to convince ourselves that whenever you have such a situation in a Bayesian network, we could say that R and S are conditionally independent on given W. And what I'm going to do in the next few meetings, I'm going to show you different situations and generally read conditionally independence from the graph. The reason I'm doing this is that there's some techniques that automatically build the structure of the graph, and they use conditional independence to do that. And that's the reason I want to do that. Go over these observation of how do you read conditional independence from a Bayesian network graph. So basically, I want to prove that this product here equals, if you look at the definition, equals the probability of R and S given W. Now, if you start with this definition, with the first one, it becomes complicated. So I prefer not to do it that way, and I'll prefer to work with the second definition. So if you look closely at the first attempt, so the probability that of R given W is the probability of R and W divided by the probability of W. Same with S given W. And then I need to start working with the marginals. So the probability of the R and W is the sum over the probability over the probability of R, W, and S, given all the possible values of S and so on. And I need to start manipulating these sums to get to my objective, that the probability of R and S given W, so that I can get the proof that they are conditionally independent. So it looks to me a bit complicated, so I'll give that up, and I'll start with the probability of S given that W and R. Maybe that will be easier. So that's the probability of S, W, and R divided by the probability of W and R. That's the definition of the conditional probability. Now the probability of S, W, and R, I can now use the network. Based on the network, as we discussed last time, this is the probability of R and the probability of W given R and the probability of S given W. This step I'm reading from the network. That's important to understand. So any network can be translated to a factorization where each probability is dependent on the parents. So the probability of W depends only on the parents, and the probability of S depends only on the parent, and vice versa. And and divided by the probability of W and R. So that is equal to this given the network. Now, so the probability of W given R times the probability of R is the probability of W and R. Okay, that's basic probability rules. So this cancels, and you get the probability of S given W, which is exactly the definition of the independence. So we've proved that given this format of a network or part of the network, given W, the probability of R and S is independent. Okay. Any questions or comments about this? Okay. Okay, so thank you very much for joining today, and we'll continue next.
Thanks, Aitan.
Thank you.
Thanks, Eitan.
Thank you.